Assalamualaikum warahmatullahi wabarakatuh. Okay, now we continue our new topic in chapter 3. Okay, part A. So basic equation in fluid mechanics. Okay, learning outcomes. At the end of this chapter, students should be able to understand and analyze basic equation in fluid mechanics and list out and apply Bernoulli equation and momentum equation. Okay, so now we look at this is a introduction for this topic. So this chapter begins the various study in aspect of moving fluids and primary emphasis that placed on the flow of fluid through pipes or tubes. So a fundamental concept used to analyze and design fluid flow system using continuity equation, momentum equation, energy equation, and Bernoulli equation. So Bernoulli equation is based on the principle of conservation of energy. It's the fundamental tool developed in this topic for tracking change in these three kinds of energy in a system. So the three energy that we have learned after this. Okay, now we look at the types of flow. They have the incompressible fluid flow that assume the fluid has constant density and the constant through liquids are slightly compressible. We usually assume them to be incompressible. Okay, the steady flow means steady with respect to time. So thus all properties of the flow at every point remain constant with respect to time. Okay, uniform flow happen when the cross-section shape and area through which the flow occurs remain constant. Okay, the path line is the trace made by a single particle. So this is the path line here. Okay, by a single particles over a period of time. So the path line shows the direction of the velocity. Okay, so continuity and energy equation. We must know that the quantity of fluid flowing in the system per unit time can be expressed by the following three different terms. Okay, we must know that the terms of the Q here. Okay, the terms of the Q is the volume, flow rate. Okay, the volume of fluid flowing past a section per unit time. Okay, the W is the weight, flow rate is the weight of fluid flowing past a section per unit time. And the M is the mass flow rate is the mass of fluid flowing past a section per unit time. So this is the three terms of volume flow rate, weight flow rate, and the mass flow rate. Okay, so the flow rate and this mean velocity actually is known as the quantity of fluid flowing per unit time across any section. Okay, so the flow rate can be expressed in terms of volume flow rate, okay, with the unit of meter cube per second. So Q is equal to A times by the V, okay, to get the volume flow rate. So with the weight flow rate and the unit is kilonewton per second, so we get the formula of W is equal to specific weight times by the area times by the velocity. Okay, and for the mass flow rate with the unit of kg per second, so we get the formula of M is mass is equal to density times by the area times by the velocity. Okay, so we get the here. Okay, based on the velocity, to get the velocity, so with the volume flow rate is Q is divided by area, and using the mass flow rate, so we get the mass divided by the density times by the area, and with the weight flow rate, so we get the W divided by specific weight times by the area. Okay, so this is the summarize these three types of fluid flow rates and give the standard units in the SI unit system. Okay, so with symbol Q, W, and M that I mentioned in the previous slide. So with the name here, volume flow rate, weight flow rate, and mass flow rate, and the definition here. Okay, and the SI unit. So the conversion factor for volume flow rate is this one. Okay, from liter per minute convert to meter cube per hour. Okay, meter cube per second convert to liter per minute, and from gallon per minute convert to liter per minute, and so on. So this is the conversion factor for volume flow rate. Okay, now we look at example 3 here. Okay, the velocity of a liquid with the specific gravity 1.4 in a 150 mm kilo pipeline is 0.8 meter per second. So calculate the rate of flow in meter cube per second, liter per second, kg per second, and kilonewton per second. Okay, with using this formula here, okay, Q is equal to AV here. Okay, the formula for flow rate, okay, using here. Okay, so Q is equal to AV. Okay, so we get the value of the times here. Okay, the area of the pipeline. Okay, pi times by the 0.075 here, because 150 you just divide by 2. Okay, so you get the value here. Okay, so and you times by the velocity. Okay, times by the velocity is 0.8. Okay, so you get the value of the Q here. So the discharge in meter cube per second. So now you convert to liter per second. So we know that the liter per second is 1 meter cube per second is 1000 liter. So 1000 liter is 1 meter cube. Okay, so you get the value here. Okay, the in liter per second. Okay. Okay, so using the mass flow rate here, so you just put the density times by the Q, so you get the value here. Okay, in kg per second, and with the weight flow rate, so you get the value here is kilonewton per second. Okay, so you just use this formula and this formula. Okay, so now we look at the continuity equation here. Okay, the mass is conserved. Okay, the mass is conserved when a fluid is in motion. Consider a one-dimensional steady flow of fluid through a pipe here. So based on the point 1 here to the point 2 here. Okay, so using the principle of mass conservation, so we know that from the mass comes in over A1 goes out of A2. Okay, so this is the concept of continuity equation. Okay, so mass in over A1 is equal to mass out over A2. Okay, so using the density of fluid times by the area 1 times by the V1 and times by the AT is equal to density times by the A2 times by the V2 and times by AT delta 3. Okay, mass in over the interval time. So we get the using the continuity equation. So A1 V1 is equal to A2 V2 is equal to Q. Okay, so we know that the Q is equal to AV. Okay, so flow rate Q is a quantity of fluid flowing per unit times across any section. So unit of volume over times, as example is cubic meter per second, meter cube per second, or cubic per second CFS here. Okay, so now we look at example here. Okay, water flows in a river at 9 a.m. The flow past bridge 1 here. Okay, at the point 1 here. Okay, flow to the point 2 here. Okay, is 37.2 meter cube per second. So at the same instant, the flow past bridge 2 is 26.9 meter cube per second. So at what rate is water being stored in the river between the two bridges at this instant? Okay, so they're just different from point 1 here to point 2 here. So you use this equation. Okay, so you just put the okay here, so just put the 37.2 minus by 26.9, so you get the value here. Okay, 10.30 meter cube per second. Okay, so the example 3.1. So the example to 3.2 here. Okay, a jet of water here. Okay, discharge into an open tank. So this is open tank. So this is open tank here. Okay, and water leave the tank through an orifice here. Okay, through an orifice, the bottom at the rate of 0.003 meter cube per second. If the cross-section area of the jet, okay, the jet here, 0.0025 meter squared, where the velocity of water is 7 meter per second, at what rates is water accumulating or accumulating from the tank? So what is the Q in this tank here? Okay, what is the flow rate in this tank? Okay, so now the solution here, we know that the Q is equal to AV. Okay, so this is inflow into control volume. Okay, and this is outflow from control volume, so we get the positive here. Okay, inflow volume is negative here, so net outflow. Okay, net outflow is, okay, the Q net is equal to Q out minus by Q in. Okay, so we get the 0.003 minus by 0.0025. This is times, okay, this is times the Q in. Okay, because the velocity times by the area, so we get the Q in here. Okay, so we get the Q net is negative sign, shows accumulating of water in the tank. Okay, so this is the solution here. So now we look at example 3.3 here. Okay, the river discharge into the reservoir at a rate of 500,000 meter cube per second, and the outflow rate from the reservoir here. Okay, outflow here, the Q here. Okay, in the dam is 250,000. Okay, 250,000 meter cube per second. If the reservoir surface area is 40 kilonewton per second, kilometer squared, what is the velocity of water rise? Okay, what is the velocity? What is the velocity here? Okay, you to find the in reservoir. So we know that the Q out here, okay, minus by the Q in here, plus the Q rise here, so we get the 0 here because this is using the continuity equation. Okay, so this one minus by 4,000 here, 400,000 here, plus the Q rise, so we get the Q rise is, okay, 150,000 meter cube per second, so we get the Q rise. Okay, from the Q rise here, so we find the V rise, so we get the velocity rise is 0.00375 meter per second. Okay, so now we look at the energy equation here. Okay, consider frictionless steady flow of an ideal fluid along the streamline as shown here. Okay, we should consider the force acting in the direction of the streamline on a small element of the fluid in the stream tube, and we shall apply Newton's second law, that is F, okay, is equal to ma here. Okay, so the F here, okay, force is equal to mass times by the area. Okay, so the cross-section area of the element at the right angles to the streamline may have any shape and varies from A to A here. Okay, this is in, flow is in, and this is out here. Okay, so this is called out, this is called in. Okay, so this is the concept. Okay, so we know that the kinetic energy here, okay, a fluid of mass with all particles moving at the velocity v possesses a kinetic energy. So kinetic energy is equal to 1 over 2 here times by the m times by the velocity squared. Okay, so for unit weight of fluid here, unit weight of fluid, so we have the velocity squared over 2g, okay, in m or feet. Okay, for unit mass of fluid, so we have the v squared over 2, and for unit volume of fluid here, so we have the kinetic energy here with the density times by the velocity squared over 2. So we have the 3 particles, okay, based on the unit weight, based on the unit mass, and based on unit volume. Okay, now with the potential energy here, okay, the potential energy of a particles of fluid depends on its elevation above an arbitrary datum plane. Okay, a fluid particle of weight W is weighted at the distance Z. So this is distance Z, and the W here weight above datum possesses a potential energy PE of PE is equal to W times by the Z. Okay, and the potential energy per unit weight here, okay, we get the per unit weight is equal to Z. Okay, potential energy per unit mass here, okay, the PE divided by the mass here, so we get the gravity times by the Z, and potential energy per unit volume here, so we get the PE potential energy divided by the volume here, so is equal to density times by the G times by the Z. So this is the per unit weight, per unit mass, and the per unit volume. Okay, so based on the per unit weight, per mass, and the volume here, so we can use this as the pressure head. Okay, a particle of fluid has energy due to its pressure above datum. So this is called pressure. Okay, pressure is equal to specific weight times by the H. Okay, so the H is also called the pressure head. Okay, so the H is called the pressure head, with the is equal to pressure divided by the specific weight. So this is also energy per unit weight. Okay, so now based on Euler's equation for an incompressible fluid with the specific weight constant, the energy per unit weight is given as KH. K is equal to pressure, okay, based on the pressure divided by the specific weight plus the Z plus the V squared over 2G. So this is based on Euler's equation, and we also call this a Bernoulli equation, Bernoulli theorem. Okay, so based on the pressure head, okay, the pressure head here, so we use the Bernoulli theorem. Okay, basic assumption. So viscous or particle friction effects are negligible. Flow is steady, applies along a streamline, fluid is incompressible, and no energy is added or removed from the fluid along the streamline. Okay, so for the case of incompressible fluid here, okay, so we use the water here. Okay, the energy per unit weight. So the unit per unit weight, this is per unit mass, and this is per unit volume. So you use this formula. Okay, density, pressure times by the specific weight plus the Z plus the V squared over 2G. Okay, this is per unit weight. Okay, when using the per unit mass, so they must include that the pressure divided by the density plus the G times by the Z plus V squared over 2. Okay, because this is based on the unit mass. Okay, based on the energy per unit volume here, so we call it as the pressure plus the specific weight times by the Z plus the 1 over 2 times by the density V squared. Okay, so this is based on the energy per unit volume. Okay, for Bernoulli equation, so we always use the energy per unit weight. Okay, so considering Bernoulli's energy equation at point 1 to point 2 here, so we use the here, okay, at the point 1 here to the point 2 here, so we must have the Bernoulli equation that using the energy per unit weight. So we use the pressure 1 at the point 1 here, divide by the specific weight plus the Z1, okay, plus the V1 squared over 2G is equal to at the pressure head at the point 2 here. Okay, so this is the formula for Bernoulli equation. Okay, formula for Bernoulli equation from the point 1 to point 2. Okay, so now we look at the application of Bernoulli equation based on refer to example 3.4 to 3.10. Okay, now we look at the example here. Okay, glycerin with the SG 1.26 flows in a pipe at a rate of 700 liters per second. At point 1 here, so the pressure is 300 kilopascal at the point 1 here. Find the pressure at point 2 here. Okay, if the elevation point 2 is 1 meter lower than point 1. Okay, so neglect head loss value. Okay, we know that the Q is 700 liter per second. You just convert to meter cube per second. Okay, and then you must calculate first the velocity one. Okay, you calculate the velocity one based on the diameter one and the Q. So we get the velocity one here is 2.476 meter per second. Okay, and then you must calculate the velocity 2 here based on the diameter of 300. Okay, so diameter of 300 and the Q is 0.7 here, so we get the value here as velocity 2. Okay, and this is velocity 1. Okay, consider Bernoulli energy equation at point 1 here to point 2 here, so use this formula. Okay, this formula for Bernoulli equation. Okay, neglect head losses value, so the head losses is 0. So we will use these head losses in topic 4. Okay, we also use the Bernoulli equation and we use the energy losses in topic 4. Okay, so now using the Bernoulli equation, just put all the value you get, the V1, okay, you get the P1 and so on. You just put here until you get the pressure 2, pressure at the point 2 here is this value 254.4 kilopascal. Okay, so now look at example 3.5. So we have the section 1 here. Okay, so with this one, okay, and the diameter 25 we at the point 1. Okay, section 1, the gauge pressure is, okay, this kilo, and velocity is 3 meter per second. Okay, at section 2, which the diameter here and the Z above section 1. So assuming there are no energy losses, so to find the pressure at 2 here, okay, to find the from the point 1 to point 2 here, to get the pressure at 2 is what value. Okay, so you must find here. So this is here. Okay, the flow is based on the inlet here to the outlet here. Okay, based on the from point 1 to point 2. Okay, first you must, okay, based on this is the data given. Okay, the data given in the text. So the specific weight of the water here is 9810. Okay, based on the specific weight. Okay, specific weight. Okay, diameter 1 is 0.025 meter. Pressure at point 1 is 345 kilopascal and velocity 1 is 3 meter per second. And diameter is 0.050 meter. Okay, and the Z2 minus by the Z2 minus by Z1 is the elevation here. Okay, Z2 minus by Z1, so we get the 2 meter here. So this is all the data given in the text. Okay, so now you must using the continuity equation. So this is called continuity equation. Okay, continuity equation. Okay, so the Q1 is equal to Q2. Okay, Q at the Q1 at point 1 must equal to Q2. So you must calculate based on A1, V1 is equal to A2, V2. Okay, so just calculate the value here. Okay, and calculate the value here. So until you get to find the velocity 2. Okay, you just put all the data here and you get the velocity 2. Okay, after you calculate the velocity 2 based on the continuity equation, so you must consider the Bernoulli equation. So this is the Bernoulli equation. Okay, so this is Bernoulli equation. Okay, so this is Bernoulli equation. So you must use consider at the point 1 to the point 2 here. So this is based on point 1. This is based on the point 2 here. Okay, so put all the value here. Okay, Z1 minus by Z2. Okay, you just put here Z2. Okay, Z2 minus by Z1 here. Z2 minus by Z1 to 2 here. Okay, and put the value here. So until you get the pressure at 2 is 3 to 9.6 kilopascal. Okay, so this is the concept that you must find the value of velocity based on continuity equation, and then you use the Bernoulli equation and put all the value in that formula until you get the pressure at 2. So now we look at the example 3.6. Okay, figure shows the siphon here, okay, that used to draw water from a swimming pool. Okay, the pipe that marks up the siphon has the inside diameter of 40 mm and terminates with a 25-meter diameter nozzle. Okay, this is nozzle here. Okay, so assuming that there are no energy losses in the system, calculate the volume flow rate through the siphon and the pressure at points B, C, D, and E. Okay, so you must find the pressure at the point B, at the point C, D, and also the E here. Okay, so first you must find the pressure at A here. Okay, so pressure at A, so because they give you the pressure at A is 0, okay, and the VA is also 0, so this must include that the, okay, this is the calculation here. Okay, first, you must find the flow rate of the pipe by equating the total energy at point AF. Okay, so you must find at energy at the AF here. Okay, so at point A, from the point A here to point F here, since the pressure at both locations are known. Okay, so we know that the pressure at the A and the F is 0. Okay, so that's why the pressure at A and the F is 0. So this is 0. Okay, because the pressure at A is 0, open to the atmosphere, and the F also open to the atmosphere, so we get the also 0. Okay, so gauge pressure at A and F are 0. So we have that PA is equal to PF is equal to 0. So we just also have this equation here. Okay, so ZA minus by ZF. So ZA here to the ZF here. Okay, so ZA is, okay, 1.8 plus 1.2 meter, so 3 meter. So ZA is 3 meter and ZF is 0. Okay, so ZA is 3 meter times by the ZF is 0 at the datum here. So that's we get the 3 meter. So that's why we get the value here. Okay, so now velocity in the tank is negligible as it is small compared to the velocity in the pipe. So the velocity in this tank, okay, negligible, so we just neglect, okay, as it's small compared to the velocity. So we get the velocity at A. Okay, velocity A is 0. Okay, so therefore, so from this one, okay, from this equation, so we get using this equation here, so we get this 0 and also this also 0, and the ZA minus by ZF is the 3 here. Okay, and also have the ZF here, so ZVA also 0. Okay, so it's just only have the VF here. Okay, velocity at F, so we get the velocity at F is this value. Okay, first you must find this value. Okay, velocity at F, okay, 7.67 meter per second. So we know that the Q is equal to A V, so area at F here, okay, is times by the velocity F here, so we get the diameter at F here, so we know that the here is 25 mm diameter, so we get the area of this nozzle. Okay, so we get the Q is 0.00377 meter cube per second. Okay, for this discharge in this pipe, okay, tank, and this pipe. Okay, now we look at the, so we know that the Q, so this is the Q that we calculate from the previous slide. So energy, so now we look at the energy between A and B. Okay, so we just put the A and B. Okay, between A and B, look at the A and B. Okay, so use the Bernoulli equation here from A to B here. So the PA, okay, pressure at A divided by the specific weight plus the ZA plus the VA squared over 2G and PB, okay, based on the A to B here. So we use this Bernoulli equation. Okay, so we know that the PA is 0. Okay, 0 also. Okay, so that's why we get the 0. Okay, and the VA is also 0. Okay, that neglect. Okay, and the ZA and the ZB is also 0. Okay, because at the same level. Okay, A and B is at the same level, so the ZA is also 0. This is also 0. Okay, so we get the 0 here. Okay, just only have the pressure at B and plus the velocity B squared over 2G here. Okay, so velocity at B, so we know that the given to you that velocity at B is 3 meter. Okay, 3 meter per second. So we put the VB as here. Okay, until you get the pressure at B is negative here. Okay, also the negative PB is 4.50 kilopascal. Okay, based on this pressure. Okay, now we know that the velocity at B, okay, velocity at B must same at the velocity at C and at D. Okay, because it's in the same flow here. Okay, so we get the Q, and with the same, because we have learned the pressure in topic 2. So based on this pressure here at the B and the C here, okay, so we use this equation. So we get the velocity at B is velocity C and velocity at D, so it's the 3 meter per second here. Okay, so we know because this is the same pipe. Okay, with the same pipe, so this must have the velocity is equal, is the same. Okay, because with the same pipe, diameter pipe with the same, and with the same liquid, so we have the velocity at this point is the same, 3 meter per second. Okay, with the same as the B here. Okay, so now we look at the energy equation, okay, between A and C. Okay, so step by step here. So energy equation between A and C, so you must using the Bernoulli equation based on from A to C. So from A to C here, so you just A is 0. Okay, we know that A is 0, also 0. Okay, and the Z and the Z, so ZA, okay, ZA is 0 at the datum here, C is 1.2 here. Okay, so ZA minus by the ZC, so we get the negative 1.2 here. Okay, based on this one, okay, we get the 1.2 here. Okay, and also the pressure at C and the VC here, so just calculate and solve this calculation, so you get the pressure at B is negative 16.27 kilopascal. Okay, so we get the pressure at B. Okay, sorry, pressure at C, not B. Okay, pressure at C. Okay, so PB is this one. Okay, so this is pressure at B. Okay, so we get the 16.27 kilopascal. So now we look at the step. We know that the VB is equal to VC is equal to VD. Okay, so the Q is equal A, B, C, D, so it's also same as the 3 meter. Okay, based on the previous calculations. Okay, now we look at the Bernoulli equation between A and D. Okay, so Bernoulli equation at A between A and D, so it's the same as we get the area is 0 here. Okay, it is also 0. Okay, and ZA and ZD also 0 here because it's the same level. So we just only have the pressure at D and the velocity D here. So we get the pressure at D is negative 4.6 sorry, negative 4.50 kilopascal. Okay, now we look at energy equation between A and E. Okay, so between A and E, so you use the Bernoulli equation here based on the between A and also the E. So A also we got 0 here. Okay, and ZA, we have that ZA is 3 meter and ZE is 0. Okay, so they have 3 meter here. Okay, ZA minus by ZE is 3 meter. So we just put until we get the pressure at E is 24.93 kilopascal. Okay, so this is step by step, okay, because we must find the pressure at this point, okay, step by step, so you get the value. Okay, now we look at example 3.7 here. Okay, a piezometer and a pitted tube are tapped into a horizontal water pipe here, okay, as shown in figure below, to measure static and static plus dynamic pressure. Okay, for the indicated water column height, determine the velocity at the center of the pipe, okay, the pipe here, okay. So now we look at the first. Okay, first we know that this is point 1 here. Okay, the point 1 go to the point 2 here. Okay, so we know the H2 and the H3 here. Okay, and this is velocity 1. So we know that this is concept for we have learned in chapter 2. Okay, based on the pressure. Okay, pressure measurement. So we use the concept here for the pressure at 1 here. Okay, so pressure at 1 here. So we have include the pressure with the density here. Okay, so we just neglect the P atmosphere, so just only have the density of this water, okay, times by the G times by the H1 here. The H1 is 3 cm and plus the H2. So this is the pressure at 1, okay. So and pressure H2, okay, pressure H2 is include the density of this fluid times by the G times by the H1 times by the H2 times by the H3. So we get the pressure at 1 and pressure at 2. So actually this concept you all have learned in topic 2. Okay. So at stagnation point, velocity is 0. At stagnation point is 0. So the velocity 2 is 0 point. Okay, because it's stagnation. Okay, so neglecting energy losses. So the energy equation at point 1 to point 2 here. So use the Bernoulli equation. Okay, this is the Bernoulli equation, energy equation. Okay, at the point 1 and the point 2 here. So the point 1 and the point 2 here. So just put the value here. Okay, Z1 and Z2 because it's the same level here. So no Z1 and Z2. So that's why we have the 0 here. Okay, and put the pressure 1 and the pressure 2 at this equation and the velocity 1, okay, because the velocity 2 is also 0, okay, because it's extension point. Okay, so we have the velocity 1. Okay, so just put the value here until you get the velocity 1 is 1.53 meter per second. Okay, so this is the calculation for get the value. Okay, so now example 3.8 here. So the venturimeter shown in figure below carries water here, okay, with the specific weight, and the specific gravity of the gauge fluid in the manometer is 1.25 here with the specific weight of 12.26 kilonewton per meter cube. So calculate the velocity of flow at section A, okay, to get the velocity for section A here, okay, to get the A here. Okay, so first you must remember, you must do using the Bernoulli equation. Okay, must use the Bernoulli equation at point A to point B here. So based on this Bernoulli equation. Okay, so now you must know that the ZA, so ZA here, okay, ZA is at the 0 here, is the datum here, and the ZB. So ZA minus by ZB, so we get the value here 0.646 meter. Manometer equating relating A and B. Manometer relating A and B. Okay, so we use the Bernoulli equation that based on the PA and PB. Okay, you just put the PA and this one KY plus the 1 point here. Okay, the density of the velocity here. Okay, actually the manometer equating relating A and B here at the point A and point B here. So the pressure at A, okay, must include the gauge here, pressure gauge based on the Y here, okay, plus the 1.18 here, okay, minus the G here, okay, inside the meter. So we get the value here, okay. until we get the PA minus by PB, because this is manometer, this differential manometer. Okay, this is differential manometer that we have learned in topic 2. So we get the value of this one and just put all the value here until you get the value of PA, pressure A minus by pressure B. So we get this value. So using the continuity, okay, so using the continuity equation relating A and B, so we have the A times by VA, okay, AB times by the VB. So you get the velocity of the diameter at the area of A and area of B, pipe A and pipe B here. Okay, the pipe B is based on the diameter of 200 and the A is 300. So we get the velocity B. Okay, so the velocity V is 0.3 power of 2 divided by 0.2 power of 2 times by the VA. So this is VA. Okay. Okay, so we get the 2.25 VA. Okay, so we know that the value of here, okay, and we get the VB here. So now after we get the ZA, ZB is negative 0. Sorry, the negative 0.46 here. Okay, so we know that the pressure difference of PA to PB here is this value. So actually this is value that we find from the previous slide. Okay, use the Bernoulli equation based on the from A to B here, Bernoulli equation here. Okay, so just put all the value here. Okay, put all the value inside this equation or inside this formula, so until you get the VA is 1.24. Okay, so after you get the VA, you just put again at the VB here. Okay, so we get the Q is equal to AV, you get the Q is 0.088. So we get the VA and V. After we get the VA, so just find the VB. Okay, after we get this one, so you just find the VB. Okay, VB is 2.25 VA. So you just put 2.25 times by 1.24. So you get the value of VB. Okay, so find the VB here. Okay, so and then you get the Q. Now we look at example 3.9 here. Okay, so compute the flow rate under the sluice gate as shown in figure below here. Okay, to get the flow rate, you must use the Bernoulli equation here. Okay, the Bernoulli equation based on the 0.1 here to 0.2 here. So this is 0.1, this is 0.2. Okay, 0.2 is below the sluice gate. Okay, so we know that the pressure at 1 here is open to the atmosphere. So this is 0. Okay, and also the P2 is also open to the atmosphere, so this is also 0. Okay, so Z1 and Z2, they have the Z1 and Z2, and we have the V1 and V2. Okay, so Z1 is 2 meter here. Okay, Z1, and that's the Z2 here. So we have Z1 minus by Z2 is, okay, 2 meter minus by 0.8, so we get the 1.2 meter here. Okay, so using the continuity equation relating 1 to 2, so we must get the Q1 is equal to Q2. Okay, this is the continuity equation. So based on this one, so you must consider 1 meter width. Okay, consider 1 meter width for these types of the sluice gate. So H1 times by the 1 is equal to V1, because we don't know the height of the sluice gate here. Okay, height of this sluice gate is 2 meter times by the 1. Okay, the H2 is 0.8, so we get the V1. Okay, V2 in terms of V1. Okay, so V2 in terms of V1. Okay, and using the Z1 V1 square over, because based on the previous slide, okay, based on this is Bernoulli equation. Okay, based on the Bernoulli equation, so you use this one. Okay, just put the velocity 2 in, okay, in the velocity 2 here. Okay, the velocity 2 with the terms of V1. So until you get the solution of V1. Okay. So after you get the V1, so you must find the Q here. Q is equal to A1 V1. So we get the Q. Okay. Q is 4.24. Okay. After that, this is the squeeze. Okay, you can do the squeeze after class. So now to be continued in part B. That's all. Assalamualaikum warahmatullahi wabarakatuh. So I will cover it in the part B.